Okay, this is acid-base free response in the essay section, and this is 1994. Okay, a chemical reaction occurs when 100 milliliters of a 0.2 molar solution of HCl, strong acid, is added dropwise to 100 milliliters of NaPO4. Okay, Na2PO4. Okay, so added dropwise, this looks like titration, but what do we have here? This isn't a base, it's a salt. But okay, so what is this strong acid going to do? So first of all, HCl is going to be doing this. Okay, and then Na is going to be a spectator, so it's not going to play. This is going to be a spectator. And so we've got NaPO4 3 minus. Okay, so what's going to react? The H plus and the PO4 3 minus. Okay, so write the two net ionic reactions for the formation of the major species. Okay, so it seems to me that we should be able to do this one very quickly. H plus, this says net ionic, that means no spectators, plus PO4, PO4, 3 minus. We could do a straight arrow, we could do a double arrow, but since they're talking about salts and acids and bases, I'm going to do a double arrow because I don't have strong of both. And this is going to give me HPO4 2 minus. Okay, now it says the two net ionic equations. Okay, well the only thing that can happen, if I'm looking at it, I can't just write this twice. That's not what's going to happen. If we continue to add hydrogens to the solution after we've made this, what's going to happen now? Some of these are going to be picking up, plus the H plus. And we're going to get ourselves some H2PO4 minus 1. Okay? So those are the two net ionic reactions that are occurring. Then it says, identify the species that acts both as a Bronsted acid, it's going to give away a hydrogen, and as a Bronsted base in the equation in A. These species, it's not saying identify a Bronsted acid and a Bronsted base. It says these species that acts as both. Okay, so this one is the wording of this. It says it acts as both of these in the equation. Okay, so what you have to understand is this. So there's only one that is able to do this. Okay, so here, this species is accepting, this HPO3 minus, is accepting a proton. So here, it's acting as a Bronsted-Lowry base. Okay. However, it doesn't show it on this, which is why this wording is a little iffy, but it could act as a Bronsted-Lowry acid. It's got a hydrogen ion to give away. And so this is the species that is going to be both a Bronsted-Lowry acid and a Bronsted-Lowry base. Because we can see it accepting, and that was sort of the trick to get you to do both of these. You see this thing that has the ability to donate an acid, to donate a hydrogen, being an acid, also being able to accept. So this is how we find these in the, and this is not an uncommon question. And you find these in the polyprotics or the diprotics. So that is the species. Now we have to draw the Lewis dot diagram. Okay, so here we go. All right, so remember, in a Lewis dot diagram, we have to build the structure using only the valence electrons. So if I go to the periodic table, hydrogen's bringing me 1 valence electron. Phosphorus is bringing 5 valence electrons. And oxygen is bringing me 6 valence electrons, and I have 4 of those. So that is 24 and 5 and 1. And then, don't forget, I've got these 2 over here. So all together, I have 32 electrons to build my structure with. Remember, I start off using the least electronegative, never hydrogen, for my central atom. And I'm just going to hang my atoms on here. What I have to remember, though, is this hydrogen belongs to an oxygen. So 3, I need 4 oxygens. And then one of these is going to have a hydrogen on it. Okay, so now let's count up our valence. So that's 2, 4, 6, 8, 10. And I have 22 left. And so I have to fill my outer. So I hung my outers. And now I'm going to fill the outers, where everyone has 8 except hydrogen, which has a duality. It's only going to have 2 electrons, and so it's done. Everybody gets 8. If you're in the 3rd group or above, you could possibly have more, an expanded octet. But hydrogen only gets 1. Once you hang it on the tree, you never touch it again. Okay, so now this is 8, and 8 is 16, and 8 is 24, and 8, this is a pair, that's 2, and that is 32. Now, on this, because it is an ion, you have to, I drew a crooked, I know, I'm sorry. You have to put brackets and put the charge. Maybe I can make this joker turn around. No, I can't. Okay, I'm sorry I drew it like that. I can fix it up a little bit. And maybe you don't even care. I don't know why it's just so much easier for me to write crooked on this thing. But there you go. All right. So that's B. And point-wise, if we were looking at this, this structure was worth 2 points. And 1 point, 1 point was for using 32 electrons, and 1 point was for having this charge out here. So there we go. Okay, and this was, A was 2 points. This was 1 point and 1 point. Okay, moving on. Sketch a graph using the axes provided, showing the shape of the titration curve that results when 100 milliliters of the HCl solution is slowly added from the burette, H plus going in. You're doing 100 milliliters, and we don't know, that's 0.1 liters, what the molarity is, slowly added from a burette into the PO4 3- solution. Okay, all right, so let me see here. Okay, all right, so this is a 0.2 molar solution. So what would I have added? Okay, well, I don't really need to know that right now, but okay, so we've got PO4 3-. So this is a salt, right? So there's the Na3s in there, but they're just spectators. Okay, so now what's going to help us, we're adding acid to it. And what's going to help us determine where we start off is, okay, remember how we determined whether a salt would be acidic or basic in solution? And we said this is the strong parent, and that came from sodium hydroxide. That's PO4, that came from a weak acid. So strong wins. So you're going to have a basic salt. So you know you're going to start high. There are no numbers here, but you're going to, it says, so all you've got in here is a high pH in the beginning. Okay? Showing the shape of the curve that results when 100 milliliters is titrated slowly. Okay. So you start high, and then, well, I should go the other way. Okay, first I'm going to back up and tell you about this. Okay, so remember, there was a reason they're leading us here. There's a reason that they put you had to write out both of these ionic equations, because after you add some of this, and you form HPO4, you're also going to subsequently be forming these two things. So you got a double hump. All right, so as you add this, the pH starts to decrease, and then it's going to, oh, I didn't mean to go up. And then it's going to buffer off again, and then it's going to decrease again. I'm going to start over. That looks terrible. Okay, so starting high, coming low, and sort of doing, remember how this is usually what we saw them look like. That's strong, strong. And then we saw like, that would be a, oh, I should be squattier. This would be the weak, weak. More like this. That's ugly. Anyway, so it starts off with this little hump. The strong, strong would be flat, straight up, flat, like really, like that. So here we've got weak. We're invading. So we're going to come down. And did you have to do this perfect? No. And are you shooting for 7? No. That is definitely not what you're doing. But once you get the first equivalence point, where you have HPO4, then, so this is called, I remember, let's see. So this would be your first equivalence point, and then this would be your second equivalence point. And remember when we said when we're adding strong to a weak, we have buffer zones, and you're going to buffer your way to every equivalence point. So those are buffer zones, and then this is a buffer zone. So you buffer, not buffer, buffer to the equivalence points. Okay, so this is a 2-humper, is basically what it is, because it is a diprotic. And so everything that you've looked at, I think just about, I think we looked at one of these on your titration notes. But if you're doing a diprotic, or they don't do these very often. And so I think I may have even said they never do them, but they do them. They don't do them very often. But I suspect that this is a good question for this 2020 exam, because it stays within acids and bases, but it tests the higher ends of acids and bases, but it's no big deal. If you get a polyprotic and they led your hand right here saying 2 net ionic equations for the formation of the major species. So they're telling you that both of these things have to happen. That's the only thing possible. And then if you're going to titrate it and you're going to make 2 species, well, then you're going to get to 1. You're going to have an equivalence point here. And you're going to buffer again and get to another equivalence point. So that's really all they were asking. And it probably would, I'm going to try to redraw this to make it look better. If I didn't try to do it all in one little bubble, so over, down, over, down, over. Okay, so then you have, that hump shouldn't be there like that. So then you've just got your first equivalence point between this part and this part, and between this extension line and this one. Oops, that wasn't a good one. And between this vertical and this vertical, I should do these in another color. This one and this one, so those are my equivalence points, because it says account for the shape of the curve. Those are your two equivalence points. And this is called, oh, not that. Undo this. Okay, from here, and this is not really flat out like that, it's kind of coming on down. This is called the buffer zone. And then buffer, because remember, you're going to buffer your way to an equivalence point when you have strong, weak titrations. Strong don't have buffers. Okay, so this is your first equivalence point. This is your second equivalence point. What is an equivalence point? When moles acid equals moles base equals moles salt formed. So here, this is where moles of the acid equal moles of the base, right here, the first one. And then the second one is when the HPO4 base is equal to these H plus moles. Okay. So points on this, there was 1 point to show that 1 point for diprotic curve, knowing you had a diprotic acid, double hump. 1 point for having the pH decrease. 1 point for either labeling an equivalence point or a buffer zone. And there's a fourth point, I thought. Maybe not. Maybe just 3 points. Okay. Let me see what we got now. Okay, I'm looking at the thing again. All right, so the graph starts high, and from the upper left, and goes right, decreases 1 point. 2 buffers in either direction is 1 point. That's right. Showed 2 trends. Okay. pH equivalent is 3 points. That's them. Okay. So that's right. Okay, and the last question asks us, okay, so the last question asks us, write the equation for the reaction that occurs if a few additional milliliters of the HCl are added to the solution resulting from the titration. Okay, in my titration, what did I do? I just converted that the PO4 3 to HPO4 2 minus. And then in the second part of this, I converted this HPO4 2 minus to H2PO4 minus. So this is what I have. So if I continue to add hydrogens to it, let me put it down here. Let's put this back. PO4, 3 minus. HPO4, 2 minus. So then HPO4, 2 minus, and I'm making H2PO4 minus 1. If I continue to add this, what past that equivalence point, what would I then form? I take this. I didn't write that though, did I? If I continue to add past that equivalence point, H2PO4 minus 1, what would I get? Okay, we need to talk about this again. Okay, now, but let's talk about this. Because I should have looked at the stoichiometry. I'm right, but I should have double-checked myself. Because it tells us that I have 100 milliliters of a 2 molar solution of this and 100 milliliters of a 0.1 molar solution of the PO4. So I've got twice as much H plus, twice as many moles as I have PO4 moles, okay? So that means I could add 2 of these. Well, by the time I do this, I'm out of the acid and I have converted it all to those species. Does that make sense? That's what they're trying to say anyway. So you would have converted all of your acid. So then, if you added more here, then you would continue your conversion and make the H3PO4. Okay, and that does it. And this question was 1 point. 1 point for this reaction. Okay. Again, I say, you go work the next ones. Don't watch me work it. You need to come back and check your answers, check your logic. That's what you need to be doing with these videos, is checking your own work, not recording what I do. So go work the next ones and come back to see the recordings. Okay.